So thank you everybody for joining today for this Sim Center research engagement meeting. So we have been doing these meetings over the years, and also we are continuing that in the next couple of months. So today, the topic is going to be HydroUQ updates, and in particular, new MPM capabilities, Celeris Boussinesq workflows, and also some DesignSafe remote jobs. And this is organized by one of the committees from Sim Center, is the Tsunami and Hurricane Group, a working group. And I am the host. My name is Pedro Arduino. And so all this is thanks to the support from the National Science Foundation and this grant that is mentioned there. And of course, all the opinions are our opinions. They are not from any federal agency or anything else. So the speaker today is going to be Justin Bonus. And Justin Bonus, he's a former student here at the University of Washington, but then he did a postdoc at the Sim Center at UC Berkeley. Currently, we are lucky to have him back in Seattle. He's working for Shannon and Wilson, one of the leading consulting geotechnical companies here in the US. And in his seminar, he's gonna introduce a little bit this HydroUQ, but in particular, he will try to show how you can use this tool, the type of problems, some validation, some verification, and looking forward a little bit for the future. So if you have questions, notice that here in Zoom, you have the question and answers button that you can use. You can add your questions. And this is good because the questions can be upvoted by the attendees. So later we can choose during the questions and answers, we can choose which one has the more votes. But you can also use the chat if you have questions. I will leave that to Justin. I think that he prefers to give his presentation and then later answer the questions. But maybe Justin, tell me if I am wrong about that. Please remain mute if you can if you are in the middle of the presentation. I have some resources for today. In particular, there is the web page for this tool where you will have the documentation, the examples, and the code itself. And there is also a GitHub page where you can download the source code for the tool, so you can really put it in your machine and compile it and so forth. If you have the executable is also available if you don't want to deal with the compilation, but if you want to see the source code, it's there. And everything is stored in DesignSafe, so it's a good idea to register to DesignSafe if you want to get this information. So I will bring this slide later so that we can, if you want to take a note of this slide. So now the feature presentation. So Justin, the floor is yours. So I will stop sharing and you can share your screen.
Okay. Can you guys see this?
Yes.
All right. Well, thank you all for joining. As Pedro said, I'm Justin Bonus. I was a former postdoc at UC Berkeley, working at the Sim Center, and I'm now a lowly junior level engineer at Shannon Wilson. So I'm happy to talk about my old work, and I hope you guys enjoy it. So I'm going to be talking about HydroUQ and how it fits into the Sim Center ecosystem. To give you an idea what you can do in HydroUQ, here's one example. So here you have multi-material large deformation simulation occurring. And I'll let this play one more time. Move on. Okay, so what are we going to talk about during this presentation? Well, first we're going to go over the Sim Center software suite and what it does. We're going to discuss HydroUQ and how it fits into it. I'm going to go over a number of interesting use cases that have happened with HydroUQ. I'll talk a little bit about whether or not support will be continuing for HydroUQ and in what form it will be. And I'll discuss how you can get involved in HydroUQ in the next iteration of the Sim Center. So the Sim Center software suite. So the Sim Center published 8 main software packages. They range from regional scale, so R2D, to local scale, such as HydroUQ. They also include things such as BRAILS and Pelican, which are a bit more specific. Now, what the SimCenter software suite aims to do is it tackles performance-based engineering. Now, the way it does that is it takes each component of performance-based engineering, such as hazard analysis, structural analysis, and it turns it into modular libraries. These libraries are filled with open source software that you can mix and match, and from that you can create a whole workflow that's customized to your needs and tackles performance-based engineering. Now, as a user, the way that this manifests is you have a front-end application, which you can download from our websites. You put your inputs into it, the backend library is handled by the software, and then you get your outputs. So it's just like any other software you've used. In a more complex granular view, you have this whole matrix here, and there's 5 primary steps that I'll leave out for the sake of time. But for each step, you have 3 different tiers of complexity. So the first is very streamlined, which we put a lot of effort into making it easy for you. And the third tier is a much more complicated tier that is meant for developers. So if you want to get to tier 3, feel free to contact us. Now, one example workflow is this. So a user might choose to download our pre-built desktop apps, import their own simulation models, modify the input script to request additional random outputs, run the workflow on an HPC supercomputer through DesignSafe, and then process results locally with Jupyter Notebook. So that's one example of a workflow that you can do in our applications. The way this happens in HydroUQ, typically for a user, is something like this. So you start with a waveflume in reality, such as the Tokyo waveflume. You configure it within our HydroUQ application. Going down, you then run simulations, where you modify random variables. And then finally, you get outputs, which you compare to experimental data and other software. You can take this a step further with damage and loss analysis in our other software, such as PDE, but we'll leave that out for now. So HydroUQ, what is it? Well, in a nutshell, it's like any other software you've used in terms of CFD capabilities. However, we've implemented a wrapper of uncertainty quantification around the software, so you can do sensitivity analyses, reliability analyses, circuit model creation, and things like that. And we've also made it so that it's completely open source and allows you to mix and match various different software packages that are available in the academic community. So that includes OpenCs, material point method libraries, and other things. Now here you have a view of HydroUQ application. This is what it looks like when you open it. And this is just to show you that it's not something unfamiliar at all. As for the features in the most recent version of HydroUQ, one thing to note is we've greatly improved usability and reliability from past versions. So if you used HydroUQ before, just know that now it's a lot better. Within HydroUQ, we have 13 vetted examples. 8 of these run locally on your computer, and 12 of these run remotely on a supercomputer. Our documentation is now comprehensive and robust and can walk you through every step of running various different simulations. And we've migrated HydroUQ to now use Stampede 3, a cutting-edge supercomputer. So if you have a DesignSafe account, feel free to make use of Stampede 3 and all of its speed. Now, HydroUQ is cross-platform, supports Windows, Mac, and Linux within reason. And if you need help compiling for any of these systems, feel free to reach out to us. Recently, we've integrated BRAILS, and BRAILS being a asset generation library for buildings at any location around the world. And we've integrated it with Celeris, which is a Boussinesq wave solver, into HydroUQ. We also have advanced 3D material point method modules in it, and OpenCs for structural analyses. And we have former functionality for OpenFOAM and GeoCloud, which we're considering re-implementing if there's user demand. So now we're going to go over a number of use cases for HydroUQ. Most of the use cases for HydroUQ so far have been focused on taking experimental facilities and making them digital. Here are 3 examples: the OCU large waveflume, directional wave basin, and the Tokyo waveflume. You can also do non-fluid flumes, such as the Lahar flume over in Oregon. And here is a video example of one of these wave flumes in action. Here we're simulating it in the material point method. We have a wave coming. It picks up pieces of debris, throws them against a structure, and then HydroUQ can couple that structure to an OpenC structure, and then put that whole thing inside a UQ wrapper so that you can do uncertainty quantification and random variable analyses. Now, that doesn't sound too different from existing CFD software. So why does HydroUQ exist? Well, HydroUQ doesn't exist to make digital wave flumes. Many software can do that. HydroUQ exists so that you can eventually have digital twins. So real digital twins, which are mostly unheard of in civil engineering. Now, this is a basic workflow of a digital twin, and it looks complex because it is. Full digital twin analyses is extremely complex, so I'll leave most of the details out, but I want to zero in on a few points. So for example, digital twins, they require validation. So looking at the validation efforts in HydroUQ, we have various pre-configured digital flumes that have all been validated. Here's the OSU large wave flume. Looking at free surface elevations across the flume, we can match wave elevations pretty accurately. Here's another video, which I'll let play out. And you can see that debris impacts against a box are well behaved. On the left, you can analyze those debris impact forces against experimental results and see that you get stochastically accurate results. And on the right, you can see superimposed debris impact simulations for different debris arrays. Again, you can look at these values closer and see that they're very accurate, so this is a well-validated digital flume. Now you can take those ordered debris arrays, make them random in HydroUQ, and do a random variable analyses. Again, these results are very accurate and you can get trends out of them. Another flume we have is OSU directional wave basin. Here you can see it in HydroUQ. And in experiments, there have been a number of experiments done on debris in this flume. Here you can see the motion of debris against a frictional plane. In HydroUQ, you can replicate these and study things such as the effect of frictional values on these debris spreading. Now, you don't just have to use material point method in HydroUQ. We also have other tools such as the Celeris wave solver. And here you have it simulating the OSU directional wave basin with a BRAILS generated inventory superimposed on the flume. And you can see the effect of different wave heights. Now, the nice thing about HydroUQ is it's very well scaling. So you don't just have to do simulations of wave flumes with BRAILS inventory. You can scale up to the real thing and do simulations of tsunamis at the actual sites where they should be happening. So this is an aerial view of Seaside, Oregon in BRAILS and Celeris. Here we have the Tokyo flume. Again, you can simulate it well in HydroUQ. Here you have the vacuum reservoir chamber releasing, create a wave. And the results again behave well. Now we've actually compared HydroUQ's performance on this case against 3 other software. So on the left is HydroUQ, in the middle is dual SPH physics, which uses SPH, and on the right is Star CCM Plus, developed by Siemens Software. Again, comparing results, we find that HydroUQ is comparable or better than these in almost every single case. Now, as I mentioned before, you don't just have to do water in HydroUQ, you can also do sand simulations. So here we have the Oregon debris flow flume from the USGS. And here you can do a side-by-side of a video of this site with the MPM simulation. So I'll let that run out. And the run out results from this tend to be pretty accurate. Now, HydroUQ, again, is a software designed for random variable analyses, so you can vary things such as friction angle and the static friction of this flume. Now, going back to our digital twin view, there's various things that you might want to do in a future digital twin that HydroUQ can help support. And this includes the physical to digital interface, digital to physical interface, and the multimedia inference required for this. So this includes things such as computer vision. So for example, there are live streaming cameras at Oregon State flumes. You can take those live feeds, do depth analyses and other things to get the geometry of the flume, and eventually port that into HydroUQ. You can also do various other things, such as using novel methods such as 3D Gaussian splatting to get point clouds, which you can then simulate in MPM. And here we have a case on the bottom left that shows a sand pile, which we took a video of, and we were able to turn into a simulation, which we were able to simulate. On the right, we have some basic generative AI, which we did with students. And we input a sentence, red motorcycle, and we were able to develop a point cloud for that and then simulate it in MPM and HydroUQ with fluids and sands packed in it. Now, digital twins also include surrogate models very extensively. Because digital twins need to be real-time or faster than real-time, it's often not possible to do full 3D simulations within them. So you have to use circuit models, and to use a circuit model, you have to develop them. So HydroUQ seeks to support that. For instance, here with the student, Trey Gower, we made graph network circuit models of the OSU large wave flume. You can see it running out on the top, and you can see braking behavior. Another thing about HydroUQ is it's very apt at facility-specific circuits and also multi-scale circuits. For instance, with students before, we have done at a hackathon a number of simulations of the USGS debris flow flume at multiple scales. So on the left, you have the experiments. Next to it, you have a full-scale simulation. And on the far right, you have what students did. They made their own small-scale experiments and then did small-scale simulations and got accurate results within HydroUQ. Now, these can be used to inform graph network circuits, again, just as I showed, so that you can have multi-scale circuit models. Now, this is useful because at an experimental facility, it can be very expensive to run full-scale experiments, so it makes sense to have maybe a tabletop size experiment inside the same flume facility so that you can do quicker experiments on the fly. Here we have the same workflow, but this is done for a water flume. Going back to the digital twin, so one of the things that people seek to do in civil engineering is similitude optimization. Basically, when we do full-scale or reduced-scale experiments, it's hard to extrapolate the findings in these smaller scales to the real events. So, for instance, a tsunami. So it begs the question of how do you extrapolate up there? Well, HydroUQ supports that. In its random variable analyses, you can do things such as Froude and Cauchy similitude scaling. And here you can see the effects of that. I'll let these run out. Here in each row, we vary the Froude scale and the Cauchy scale so that you can see the effect it has on the wave. HydroUQ also supports near-regional scales. So for instance, here we're looking at Ventura, California in the Celeris wave solver, and we pair it with the NOAA sea level rise viewer. So you can get the effects of sea level rise, apply it to your Celeris wave solver simulations, and then from there you can get analyses on structures. So you can determine the effects of something such as sea level rise on a structure. We also have recent work done by Yi Sang-ri, who's at Rice University, and she looked to study the effect of near random debris fields in HydroUQ. So she varied the count of debris, the angle of debris positioning, and the porosity of a debris field. And as a result, she got simulations like these. So on the left, we vary the fabric of a debris field, throw it at a wall, and on the right, we vary things such as material properties of a debris field. From this, she was able to retrieve things such as force, impulse, and duration of impacts, which they look like a mess of data, but from these, you can actually get trends across various different independent and dependent variables. So using HydroUQ, she was able to get meaningful trends in chaotic systems. So those were all the use cases of HydroUQ recently. What about continuing support? So as you all know, research funding in the US right now is very tenuous, and funding for the Sim Center is not what it used to be. Now, there are plans for the Sim Center to get a revival and for more funding packages to come through, but in the meantime, the best way to get support for HydroUQ is either contacting myself, Pedro, or Frank McKenna, but it's also to look at the documentation that we've written. So it's very comprehensive and robust. It covers all features and examples. The example is number 13, so there's many to get you started. And it also talks how you can run this on both your local system, HPC supercomputers, and stream it through remote DCBs. There's developer documentation if you'd like to get involved in the development of HydroUQ. There's also a detailed architecture description if you'd like to know more about the SimCenter ecosystem. So getting involved. Let's say you have a feature request. You want to bring GPU accelerated GeoClaw into HydroUQ. Now that could be something that we do in the future, or it could be something that we aid you in developing. Either way, just reach out to us if you have any ideas. We love to see engagement. Again, contact Frank McKenna, myself, Justin Bonus, or Pedro Arduino if you'd like to get involved. If possible, attend the NEARI Computational Symposium 2026. I believe it's in May. And for a first step, sign up for a DesignSafe and TAC account at the links I give. I'll hold it here in case anyone needs to take a screenshot for the links. And then that's the end of my presentation. We're now going to be moving on to live questioning. I believe the video stream will cut around here, but if anyone would like to participate in live questioning in the future, please register for our events.